so that we get to maybe 1 or 2 bounding boxes per image. Once we have all that, we then have to make some kind of decision. We have to do something with that information. So if you look at the entire pipeline and you talk to, especially people who are involved in machine learning, they generally only look at this one single part, the machine learning model inference, and they worry greatly about the speed of that machine learning model inference. But we really need to look at the entire pipeline. We need to look at the speed of each part, and if it is a pipeline, it will run at the speed of the slowest part, and that may or may not be your model inference. So each part of this pipeline needs to be treated in a different way. There's no one size fits all kind of solution for an entire pipeline. You'll need a heterogeneous architecture to deal with this complete pipeline. So what we did in SiMa was to come up with an SoC device, which is based around several compute units. There's 3 principal ones. There's a number of different IOs that you would find on most SoC devices. But what we really need to focus on is those 3 principal heterogeneous compute units. So we've got a single instruction multiple data image processing block. We've got a machine learning acceleration block and some generic CPUs. Okay. We also have an extremely powerful external memory interface. One of the limitations of any hardware accelerator for machine learning or for machine vision is bandwidth towards external memory. Nearly every pipeline you will run will struggle to fit into internal memory. Now, we have a lot of internal memory in our machine learning accelerator in particular, but we will always come across cases where that just simply isn't enough. And we will spill over into external memory. Okay? So a high bandwidth pipeline to external memory is vital. And we have a 128-bit pipeline out to external DDR. And that pipeline is running at around about 3.7 gigatransfers per second. We also include in the device, the video codecs. So the video H.264 and H.265 decoding and encoding is built into the chip. Now that is something that is part of many pipelines, especially if the source of the imagery is an IP camera. The IP camera itself will compress the imagery to stream it back over the network. And if we're going to receive that, we're going to have to be able to decompress it. And then if we want to send it back out, we're going to have to be able to compress it again. And that is why we have those codecs. It's also why we have 4 gigabit Ethernet max built into the chip, so that we can easily connect up to multiple IP cameras or connect up to multiple networks and stream video in and out in a very efficient way. We also have a PCI Express bus interface. It's a generation 4, 8 lanes, so a really high power, high bandwidth connection. And we can stream data and imagery in and out of the chip over PCI Express. And that allows us to make PCI Express cards with this chip and use them as acceleration devices within things like desktops or industrial PCs. We actually sell the chip itself for anyone who wants to make just a custom board, but we do sell the boards as well, PCI Express boards, for anyone who just wants to buy a board and run with our software. So if we look a little bit more in detail at those three heterogeneous compute units, and why did we come to this choice? It'll become clearer in a minute when I explain how the pipeline maps to the device. So when you come to the decision logic at the end of the pipeline, nothing lends itself better to that kind of what if then else scenarios that you take with decision logic than a generic CPU. The generic CPU is made for that kind of operation. Okay? Now, there's nothing in our device that stops you from running image processing on the ARM-E65. A number of our customers actually just simply run OpenCV on the ARM-E65 in our chip. That's fine, but that's not why we put it in there. We put it in there mainly for control logic and decision logic. Then when it comes to OpenCV-like functions, we included a 4-core vector processor, very high speed, single instruction, multiple data. So it's highly optimized for pixel level operations, repeating the same instruction and the same operation on multiple pixels within an image. 4 cores running at a gigahertz, extremely powerful. And we provide a library of kernels, of functions that are, let's say, OpenCV-like, that you can use directly on this image processor. So within our pipeline, this is the block that we would use for image pre-processing and image post-processing. Then the block that kind of excites everyone is the machine learning accelerator itself. So our machine learning accelerator is extremely powerful. It's 50 TOPS, 50 teraops per second. It's basically follows the same pattern as a lot of these devices, a lot of these blocks. It's an array of tiles of computational multiply accumulates, but with multiple levels of memory, small local memory for each multiply accumulate block, a larger secondary level of caching for groups of those blocks, and then finally some level 3 caching for the entire machine learning accelerator. So having that level of memory within the machine learning accelerator is what allows us to keep most of that model on chip. As I mentioned before, we will always run into cases where it spills over into external memory. That's inevitable. And that's why we built in the 128-bit high-speed external memory pipeline. But this is a 50 TOPS block, and typically it's consuming in a range of 4 watts. Okay? So that's an extremely good frames per second per watt number. It's one of the best on the market. You'll struggle to find something better than this on the market right now. But, okay, so I talked about why it's important to accelerate the pipeline, but I know from experience, working with customers, that I can explain as much as I want why it's important to accelerate that pipeline. And then the next question will always be, how fast can you run ResNet 50? It's always the question that comes. It appears to become the kind of benchmark for these acceleration devices. We're no different from everyone else. We do provide those numbers. I've just kind of cherry-picked a MobileNet V2 here. So this is MobileNet V2 running on an ImageNet dataset, 224 by 224. You can see that our machine learning accelerator is actually capable of running in multi-batches. Okay? So many of our customers are focused on batch 1. They want batch 1 because batch 1 gives them the lowest latency. And they're generally trying to run something in real time. Any of our automotive accounts, any of our automotive customers are just 100% focused on batch 1, lowest possible latency. But we can run, on our machine learning accelerator, we can run bigger batch sizes. So just looking at what it gives you a much higher throughput, okay? So I'm just seeing here that, batch one, we're running somewhere around 2,000, 2,200 frames per second, somewhere around here. I can go up to batch 32, and I'm getting close to 15,000 frames per second. I actually stopped the graph here. It will run up to batch 50, and it'll break through nearly to 20,000 frames per second. Okay? So when you're looking at these devices and trying to find out which one fits your application, an important question that you ask your supplier or your potential supplier is, what's your throughput over multi-batches? Okay? If you are high latency and latency is the only thing you're interested in, it's probably batch one that you're interested in. But if you can support higher latencies, then you will get much higher throughputs if you can go to higher batch numbers. Okay, so we've seen the architecture of the chip. We've looked at a pipeline. And to bring those two things together, you can see that our pipeline here, I've chosen this pipeline here, how it maps virtually one-to-one. The functional blocks in the pipeline are mapping to the silicon blocks. So the RTSP stream receiver maps to the Ethernet max. It will also use the A65s for some software protocol stacks. The H.264 decoding maps to our codec. The image preprocessing maps to the vision processor. The machine learning model inference maps to our accelerator. Post-processing maps to the vision processor. And the decision logic maps to our generic Cortex A65 processors. So the pipeline is mapping to the silicon, and that is why we made the silicon in this way with the different heterogeneous processes. Oops, sorry. Bringing all this together requires some form of software, requires some form of development kit, and we are developing a browser-based graphical pipeline builder. Now, right now we use GStreamer under the hood. We allow our customers to build GStreamer either with C++ or with Python. But we're also building this graphical tool that allows basically a drag and drop way of going into libraries, pulling the plugins into the canvas and connecting them up and configuring them. So building your pipeline becomes like drawing, okay? You can see that there are plugins that we supply that match to our silicon. You can also bring in your own models. So you've trained your own model for your application. You can bring it into this tool and use it directly in this tool. Now, these pipelines that I showed you, even though they're mapping to different blocks, generally don't execute in a sequential manner. It's really important to us to be able to schedule the use of those blocks. So we have our own patented scheduler in our runtime that schedules at two levels. It schedules the operations on the machine learning accelerator, the different layers of the model, and then we schedule the entire pipeline across the blocks, the A65, the EV74 vision processor, and the machine learning accelerator. So we're scheduling across those blocks. And within our tools, we provide you with ways of seeing how that scheduling is happening in your pipeline as you're drawing it down. And we'll give you also, obviously, some throughput numbers, estimations, even before you reach the board level kind of design and test. So just to kind of sum up, accelerating a complete vision pipeline can't be done just by accelerating the model. You have to accelerate everything in that pipeline. And it can't be done with just an accelerator and a generic CPU. You will need some form of dedicated vision processor to work on those images at a higher level. So just to kind of close here, that is what we are providing. That is the value that SiMa is bringing to the embedded AI space. Acceleration of the entire pipeline, not just the model. Okay? So I'll close there and I'll take questions in a second. If you need more information, we're actually on the Arrow booth. We just signed a distribution agreement with Arrow, so we're on their booth today. So I'll be there if you want to come and see me and get some more information. Okay. Thank you very much for your time today. Thank you.
And what I would just say is if anyone has any questions, we do have a few minutes. If anyone wants to put their hand up and ask any questions of Mark while he's here. I saw lots of nodding heads and people taking notes and things. If there are no questions for now, here we go.
I'm assuming that your pipeline allows different machine learning algorithms or models, correct?
Yes.
And if that's so, most of the machine learning needs training. Where does this occur or happens on how do you allow
okay,
that?
that's actually an excellent question. So the question is, where did these models come from that we're running on our machine learning accelerator, and how did they get in to the device? So part of our toolkit is dedicated to ingesting trained models. We can ingest models from TensorFlow 1, TensorFlow 2, TensorFlow Lite, both floating point and quantized, PyTorch, Onyx, MXNet. We can ingest any of those, bring them into our toolkit. They will be compiled into basically a set of instructions and data, a binary file that runs on the machine learning accelerator. Okay, so basically we take the trained model, we compile it into instructions and data, and it runs on the machine learning accelerator in that way. We don't do the training. If the question is, do we do the training? No, we are totally dedicated to the inference and building of pipelines. The training we leave, between TensorFlow and PyTorch, I don't think there's any room space for anyone else to come in and make a training framework. So that we don't do that part. We focus completely on the inference.
Fantastic. Was there any other questions that our people are poised? What I would say is over here, just while you're looking at this QR code on the screen, this is for you to get your CPD credits.
Hi, I wondered if you considered working with camera manufacturers to get rid of the left-hand half of your chip and put the inference work on the back of the camera.
So the question is, have we considered working with camera manufacturers? We've not only considered it, we do it. We do have camera manufacturers amongst our customers. The current generation of device that I've showed you today is perhaps not the best architecture for putting inside a camera. We've announced the tape out of our second generation device. We haven't released technical details yet, but it will be much more amenable to being placed inside a camera.
Fantastic, a little bit cryptic. Any other questions, guys? Otherwise, you can catch Mark around the exhibition and also on the Arrow stand.
I'm on the Arrow stand.
So hold on. Right, another question at the back here. I shall wander over.
Hello. I was just wondering, in terms of the architecture that you showed earlier, where do you often do the most optimization for? Where does optimization mostly occur from the use
optimization
cases?
of the models themselves?
Yeah.
So the optimization of the models, if we have the same definition of optimization, doesn't actually happen in the silicon. It's happening in the software. So the optimization of the trained model as we get it is happening in the software. We will optimize as we are quantizing and compiling, and try and obviously, one, optimize it for our architecture, and two, try and make it as fast as possible. And that generally means optimizing it such that it uses the minimal amount of memory as possible. As always, as I said already, we do never want to spill over into external memory. We've put that massive, great memory controller there for when that happens. But anytime a hardware accelerator spills over into external memory, you'll take a performance hit. Absolutely, 100%.
Thank you.
Thank you very much. Anyone else question-wise? Otherwise, let us put our hands together for Mark and say thank you very much. Thank you.